and this is Vodcast 5D. In this video, we're going to talk all about salts. So what is a salt? It's a very general term for any ionic compound that has ionic bonds. So anytime you gain or you lose electrons, it's going to be an ionic bond and therefore a salt. The only things that aren't considered salts are when your anions are oxides or hydroxides. But any other charged cation, anion combination is going to be an ionic bond and therefore a salt. So cations and anions, they bond together. We talked about this already in small whole number ratios. Why whole number? Because what are we doing? We're exchanging, we're giving, we're losing our electrons, so it has to be a whole number. And we want to get up to 8, so that tells us how many electrons we want to gain or lose. Salts do not exist as individual molecules. They form this big structure called a crystal lattice. Crystal lattice looks like this. If you can see that. If not, I'll show it to you again when we come to class tomorrow. It has red, this is exactly table salt, it has red and white ions that form together in a nice little structure of the different ions. So really, we're taking the ratio, the simplest ratio of your cations and anions, and we call that the chemical formula. So they're not called molecules, they don't exist together. They're either called formula units or unit cells, because they're not individual molecules, they're in these big crystal lattice structures. So the simplest ratio we either call the formula unit or the unit cell. Now, why does this big structure stay together? Well, it must be, has to do with this thing right here that says Coulombic force. It must be that the forces of attraction, the positives attracting the negatives, must be a lot stronger than the force of repulsion, which again, if you think of a magnet, would be the negatives repelling with the negatives, or the positives, the cations repelling with the other cations. How does this form? Well, there's many steps. 1, 2, 3, 4. There are 5 different steps for how a salt is formed. First thing, your cation, sodium, solid metal sodium, has to change into the gas phase. Solid to gas, we said that was endothermic. You had to put energy into, you had to add energy to change an ice cube into a vapor, right? To change anything from a solid to a gas, you have to add energy. So that would therefore be endothermic. Well, what else has to happen? Chlorine here is diatomic, but when I form salt, my formula is NaCl, not Cl2, so I have to break apart that diatomic. Well, the diatomics, when they break apart, that requires energy as well, because they're more stable in their diatomic state. So this is still an endothermic part of our process. Then what do we have to do? Sodium gas here was neutral. I have to remove an electron from sodium gas to form my cation. Removing that electron also costs a little bit of energy. I have to put energy in to remove that electron. Here's where it really happens. When chlorine sees that extra electron, it wants it really bad because it has 7. So if it gains that 1 electron, it's finally stable. So energy is finally released as exothermic right here. So our first 3 steps had to be endothermic. We had to put energy into to get up until this point. When chlorine, neutral chlorine, sees that electron, he's going to snag it, and that's part of our exothermic process. The final step, part 5, when this cation, sodium in the positive charge, and chlorine anion, chlorine with a negative charge, when they finally find each other, the positive and the minus, the negative and the positive, they form solid table salt, I'll show you a video of this in class, remind me, a huge amount of energy is released when sodium cation finally reacts with the chlorine anion. So overall, this whole process is very exothermic, but in order to get to that point, a little bit of energy has to be added in steps 1, 2, and 3. When salts form, a very large amount of energy is released. It's highly, highly, highly exothermic. So when you release a ton of energy, now this lattice is very, very, very stable, which means it would take a ton of energy, called lattice energy, it would take a ton of energy to break that lattice apart. It's very, very stable. You have to add a ton of energy to this lattice to break it apart. Now, what is this crystal lattice? Well, there's some kind of ordered arrangement, positive, negative, in this case of sodium and chlorine. There's always a geometric structure. It always forms a nice geometric, evenly shaped structure, and it's a result, again, of a highly, highly exothermic reaction, so it's very, very stable. What's this lattice energy? Well, we said it's the energy that's released when the lattice forms. It tells you how strong it is. How does it tell you how strong it is? Well, the bond strength, if you have a high lattice energy, it's very, very, very stable. It means your bonds are very, very strong. If you have strong bonds, that means your melting and boiling point are going to be super high. It's going to take a ton of energy to break those very, very strong bonds within your lattice energy. There are two things that can affect lattice energy: the charge of the ions and the size, the distance between nuclei. Let's look at those things. What will affect your lattice energy? The charge of the ion. The higher the charge of the ion, the higher the lattice energy. This would be stronger. So stronger things would say, if I had a 3 plus and a 3 minus cation and anion, and they were bonding together, that would be much stronger than a 1 plus, 1 minus, because these guys are only exchanging 1 electron. In this case, we're exchanging 3 electrons. The higher the charge, the higher the lattice energy, therefore the stronger the bonds. The distance between the nuclei, if it's smaller, we talked about this in Unit 4.2 with our radius, the smaller the radius, the smaller the size of the atoms, the higher the lattice energy. Why? If they're smaller, they're closer and they're harder to separate. Think of the Red Rover game. If everything is packed together closer, it's going to be harder, it's going to take more energy to break it apart. So let's look at these two examples. This could be a possible quiz or test question. Let's call this sample A, and these three will be problem B. If I have sodium chloride, NaCl, and sodium phosphide, Na3P, and magnesium chloride, MgCl2, who would have the strongest, the highest lattice energy, and who would have the lowest? Well, always look at this one first. This will be the easiest to figure out. Always look at your charges first. In this case, sodium's a +1, chlorine's a -1. Na3P, oh, there's 3. That means it's a 3+. Phosphate is a 3-. And magnesium, it's an alkaline earth, is a 2+. If I have 2 halogens, that's a total of a 2-. So in order from weak to strong. My strongest one here would be Na3P. My weakest one would be NaCl, and magnesium chloride would fall in the middle because it's a 2 plus 2 minus. If we look at sample B, you'll notice that this is sodium plus 1, minus 1, sodium plus 1, bromine minus 1. Cesium is also a plus 1, chlorine's a minus 1. So now I can't tell based on the charge of the ions because everybody is a 1. So now I have to look at this second thing, the distance between the nuclei. If I want the strongest ones, remember the strongest ones are going to have the smallest radius. The weakest ones are going to have the largest radius. Well, I could compare my cations, sodium and sodium, they're going to be exactly the same. Cesium, when you find cesium on the periodic table, look at the alkali metals, go the whole way down. Cesium is huge. Remember, radius increases as you're going down. So our weakest lattice energy is going to have to be cesium chloride because cesium is the largest. Now I can compare chlorine and bromine. Looking on the periodic table in the halogen column, chlorine is above bromine. That means chlorine must be smaller. So in this case, NaCl is actually going to be our strongest of these three in example B because it has the smallest radius, with sodium and chlorine being the two smallest out of this group. The smaller the radius, the higher energy. The nuclei are closer, they're harder to separate, it takes more energy to break them, so your lattice energy is much higher. But more importantly than that, you can look at charge. The higher the charge, the higher the lattice energy. Look at charge first. If they're all the same charge, then look at size. Charge will be easiest to figure out first. Melting point trends. Using your knowledge of ionic compounds and lattice energy, explain the trend for the following melting points. These are all sodium. What's changing? They're all halogens. Chlorine, bromine, and iodine. As you go down the periodic table, what's happening with my melting point? 800, 750, 622. As you go down the periodic table, the melting points are decreasing. Why is that? My melting points decrease as I go down because, as we learned in the periodic table chapter, my radius, or the size, increases as you go down. So the larger the atoms, the weaker the lattice energy. It would take less energy, these guys would melt first, to break things that are weaker or larger. They can't hold together as tightly as something that would be smaller and more compact. Final thing, let's review some ionic compounds and their common properties. You will need to know some of these, but they should make sense to you if you think of the most familiar ionic compound known to you. If you think of salt, we know that's NaCl. We've already gone over the fact that it's neutral. Your pluses and your minuses, your anions and your cations have to balance out. They balance out in whole number ratios because of our gaining and losing of electrons. Thinking physically about table salt, it's hard. It would be very brittle if you took a hammer to it. It has a very high melting point, 800 and some degrees Celsius, as we saw in the last slide. So it's therefore a solid at room temperature. We've talked about the fact that solids do not conduct electricity. Why? In order to conduct electricity, you need charged particles that can do what? That can move. In order to make your particles able to move, they have to either be in the liquid or dissolved in water aqueous form, and then they generally will conduct electricity. So why? What's the difference? You have to have the charged particles. They must be able to move. Common ionic properties, naming, salts, acids, ionic compounds, back to the basics. Sounds like we're done with Unit 5. Take a look at the review sheet, see what you don't understand, and come to class with your questions.